Okay, good morning everybody. First things first, we won't be meeting on Wednesday. I have a meeting in Charleston, so our class is going to be delivered online. I'll put that lecture video on. I'll put the link on Blackboard and also send you an email with the link. Homework number 3 is available now. It's posted on Blackboard. It's related to StormCAD, which we're doing today, and stormwater detention, which is the subject of Wednesday's recorded class, and it's what we'll cover on Friday. So that assignment's due a week from today. Any questions related to the announcements? All right. We're going to skip over kind of just a review example that you may see in the notes having to do with the rational method, and we're going to jump straight into the stormwater illustration. I want us to get as much experience with that today as we can. Before we do it, are there any questions just in general, concept related, having to do with the rational method or time of concentration? Just any quick questions before we get into StormCAD? Yeah.
Can you give a quick review of like time of concentration versus the time of duration? Sometimes they're the same.
Mm-hmm. Sure. Yeah. I don't know if it'll be quick, but let's pull up the spreadsheet and go over that because it's an important point. Let me see if I can find that example. All right, so you're asking the difference between the time of concentration and the time of duration, right? So where it really comes into play is in a pipe like C, where their water is coming from 3 different locations. And so remember that in this example, the water was getting into pipe C either directly from this inlet that's connected to pipe C, or the water is coming from pipe B or pipe A. So what that means is that there's 3 possible times of concentration that could be like the governing one that we use to size pipe C. And the way that we analyze what are the times is there's the direct surface flow time that would apply if it is the water that's going into 2.1 that's the longest. And what we're looking for is which time is the longest, because it's the longest time that we're going to use in the intensity, duration, frequency curve. Now, the water that gets into pipe C via pipe B has the surface travel time and then the pipe travel time. And so here's where we'd put the surface travel time, and then this is the pipe travel time. And so we then do the same thing with pipe A. And so then there's 3 different options. The total time of concentration, it could be what's getting in directly, what's getting in through pipe B, and what's getting in through pipe A. And then this T sub D would be the longest of the 3. And the reason for that is that the worst case scenario as far as peak flow is when all of the area in a watershed is contributing at once. If this parking lot, just as an example, if it takes 10 minutes for all of the water to finally travel to that point from all of the contributing areas within that watershed, that 10 minutes is going to have a higher peak runoff than how much area is contributing during a 1-minute event. Within 1 minute, only a small region is going to be contributing the flow. And even though the intensity is higher, this is the important point, even though the intensity is higher, the overall peak flow would be less. So that's the quick overview. I think that maybe today's example, since we use the same network, may help to reinforce it, I hope. So what we're going to do is we're going to use this same structure as we worked with the spreadsheet, and we'll see if we get the same answer in terms of what pipe size is required. It's something that I think is a good approach. Anytime you're using a new method, an automated method, give it a reality check with an old method that's maybe more labor intensive, but one that you know is reliable and you understand all the equations that go into it. And so what we're going to do is we're going to kind of like take a tour through StormCAD and solve this to find the required pipe size. And then if you look at the homework assignment that you need to do, it's that same network, but more of it. And so you'll recognize here's pipe A, here's pipe B, here's pipe C. So this would be really labor intensive and complex to do with a spreadsheet, but with with StormCAD it becomes not negligible, but certainly a lot easier. So I hope that the example gets you prepared for doing the same thing with the homework assignment. All right, so here's our network, and I've given you a handout this morning that has some important information on it. Let's just look at what is in that handout. So the handout includes this stormwater data. Okay, so it's the same duration intensity curve that we've seen before, and I've got the times and the intensities, because we'll have to put that into StormCAD. We'll have to kind of recreate that curve in StormCAD. We have contributing areas as a table, so that is the area that's contributing to flow at each of these junctions. And then elevation data, and so this is the elevation of the invert, which means the bottom of the pipe at each location. And then we have the pipe length, the pipe slope, what's upstream, what's downstream, and then the elevation of each of those junctions. Now I'll point out one other thing that I haven't mentioned in the previous times we've looked at this illustration, is that we have the ground elevation as well. And so look at these contour lines, 735, 730, and so on. That's saying how high the ground is. And so if you compare that to the inverts of the pipe, what we're saying is that the, just for example, at 1.1, the pipe invert, the bottom of the pipe is at 730.5, but the ground there is at saying 732.3. So there's not a lot of cover on the top of those pipes. The main thing that we will see is that if you don't have the ground above the invert of the pipe, you'll get an error message from the program. It won't let you put the elevation of a pipe above ground. It needs to see that the pipe is buried. All right, so start up if you have StormCAD available. Start the program, and then the first thing we're going to do is check the units. We did this same thing when we were using water gems. We wanted to make sure that the units were consistent with what we are using, and in our case the example data that we have is in traditional units. So the area is in acres, for example. The stormwater data table is in inches per hour. And so here in StormCAD, if we go to Tool, now this is a completely new layout since the last time I used it, so you'll have to be patient as I'm kind of learning at the same time as you are. Tools, More, Options, Units. Alright, so it's in US Customary already. That's good. That's what we're going to use. Alright, so OK. Now what we do is we just kind of draw a schematic representation of our network. So you have the handout in front of you. What I'm going to do is I'm just going to draw a sketch, and it's not a scaled drawing. If I wanted, I could import an image in the background, but this isn't going to be a scaled drawing. It's just going to be a schematic representation. And so what I'm going to do is I'm going to draw a junction, another junction. I'm going to represent this, and the only thing that isn't on the picture that I am going to draw is an outfall, which means you have to tell the program where the water's coming out. So that's something that I'll add that isn't necessarily pictured yet. All right, so first things first, go back here to the Home tab, and then you can see that we have a lot of these familiar tools across the top that you may remember when we were doing WaterCAD last semester, just the introduction to it in fluid mechanics. But the layout button is what you use to start drawing a sketch. And right now, if I click, it's just going to place a junction. But what I want to do is right-click. Rather than just a manhole, I want it to be a catch basin. So it has to be a catch basin for the water to get in. All right, so I'm going to drop a catch basin here, and that would be 1.1. I'm going to drop a catch basin here, that's 2.1. And I'm going to drop one here, 3.1. Now I'm going to do right click and change it from catch basin to outfall. And that's where I'm telling it the water flows out. And so I'm just going to click there and now escape. So you can see 1.1 to 2.1 to 3.1 and then some outfall. Now I need to do pipe B. So I'm going to right click again, catch basin, click, and then click right on top of catch basin 2. If I click right on top of it, it won't create a new one. It'll just know to connect them. The order that you click is important. It assumes that you're working from upstream towards downstream. So the fact that I started here at catch basin 1 was significant. It was saying this is the upstream part of the network, and you can reverse it manually, but by default it's assuming a direction consistent with the order that you're clicking. And that's why when I was here at 2, I then didn't go to the left, is because then it would think that the water goes from to the left towards that other junction. So that's why I went in straight line, and I was always building the network downstream. Alright, so here's my schematic representation. What I'm going to do is I'm going to rename everything so that it's consistent with what I have in the drawing. For example, I don't want to call that catch basin 1. I want to call that 1.1, just so that it's easier to type the data in. And I can do it by selecting an item, double-clicking, and bringing up its properties. There it is. So I could rename that, instead of CB1, I could rename it 1.1, enter, and you'll notice that now it's dynamically updated that annotation on the screen. But that's not as efficient as if I open up the flex table. So here at the top of the ribbon, if I click the down arrow and open up, let's open up the catch basin table. Now I can rename them without having to open each element individually. Alright, so catch basin 2, I'm going to rename that to be 2.1.
How did you pull the flex table?
How do I what?
How did you pull up that table, the flex table?
At the top on the ribbon, if you're under the Home tab, then flex table, catch basin. Alright, so CB3, we can rename that 3.1. CB4 is 1.2. Now while we're in here, we might as well input some of the rest of the data that we know. And by the way, I want to check and see, we may need to add some additional columns, but let's put in what we know. For example, the ground data. Now, the ground data isn't really anything that's going to affect the analysis of the capacity or the sizing. Not at the level, like we're using this only for the pipe size. You could also use StormCAD for sizing the gutter, like to know how much water the gutter itself is carrying. So if you look at the invert elevations, like all of our pipes are going to be at 730 or less. I'm just going to call the ground elevation, I'm going to do 735 for all of them, because I just want to make sure that the ground elevation is above the bottom of the pipe, so I avoid any error message. Now you could take the time to actually interpolate and put in the actual ground elevation, but what I'm saying is it kind of doesn't matter. The invert elevations, though, do matter a lot. So let's put in the inverts that's actually in the handout, the table. So what we're going to be copying over is this data, the invert elevation. So that's talking about the bottom of the catch basin. So the catch basin is kind of like a graded inlet and then a big concrete box. And so this is saying the bottom of the concrete box has what elevation? So 1.1 is 730.5. 2.1, 722.7. Now you'll notice that the order of the elements here is different than the table. So don't just type it in the order that you see it. Make sure that the elevation matches the junction that you're talking about. 3.1, 718.36, and then 1.2, 723.45. All right.
So what's our ground elevation again?
I put 735 for all of it. And the point is you just have to make sure that it's high enough that the pipe isn't going to be above the ground. We just need the ground to be above the pipe. Okay. Okay, full capture. Now there is a column title called inlet location, and we may need to add a column to the list here. Let's see. Edit. Inlet location. Okay, inlet location we want to add to our list. It's not on the default list of columns, but the way that you add it is you go to this little pad that's at the top and click on edit, and then when you do, these are all of the columns that could go into your data table. I mean, all of those data fields are in the database, but they're just not all pictured when you open up the flex table. And so the one that I wanted to add, and that you should also add, is inlet location, because we may need to override that. There's a few little weird things about the program, and in the past I've had to change what we set for the inlet location. Right now it's set to on grade. I think what we want to do is put in sag, and the reason for that is that this program has the ability to estimate how much of the water that flows over a metal grate actually goes in. You know, if you have water flowing through a curb, not all of the water will go into the catch basin. But since we're not going to be defining the geometry of the curb, like how tall the curb is and what's the angle of the concrete that matches up, we just want to assume that all of the water goes into the grate, and for a small size storm that's a pretty good assumption. So we're going to change the inlet location to in sag to force full capture. It's just one of those things that's because we're not building all of the things into this network that we could, since we're not using all the functionality, we have to force some simplifications. Alright, so did everyone add the inlet location column and get it to say in sag? Alright, so the next thing we're going to do is we're going to put in the correct names and information for the conduits, for the pipes. So just like before, if you want, you could select, double click on an element and bring up its properties table, and then rename, for example, conduit 1, we're going to call that A. Oh, I've clicked something wrong. So if you double click, bring up the properties table, so this is pipe A, for example, and it knows that the start is 1.1 and the stop is 2.1. So that's the directionality that I was talking about earlier, you know, the upstream and the downstream node. Let's look through the other stuff that we want to tell it about the pipe. For example, the diameter. Now, we're doing a design, so we don't know how big the pipe needs to be. So it's saying the default diameter it's assuming is 12 inches. So we'll leave it at that. Maybe we'll increase it later, maybe we'll decrease it later. Here's the material type. You know, it's 0.013, which is the material type for concrete, saying it's a circular pipe. We have the upstream elevation, the downstream elevation. The thing that we haven't told it yet is the length. Let's just open up the flex table for the conduits and do it with a user-defined length. And hopefully you remember back when we were using water gems, having to do the same thing, where where you click on the screen kind of gives it a scaled length assumption. Like right now it assumes the length of pipe A is 67 feet, just because I clicked on one pixel here and then the other catch basin was a certain distance away. But in our data table, what we know about conduit A is supposed to be 390. So the way that we can get over the fact that it assumed some length that isn't correct is if we do as user defined length, now we can type in the length of 390 feet that we know is accurate. Okay, so let's do the same thing. Let's rename each of these conduits the name it's supposed to be, and then give it the length that's known. So conduit A, for instance, conduit 2 is what we call C. So pipe C is the one that goes from 2.1 to 3.1. Conduit 4 is B. And then conduit 3, I'm going to call it the outfall pipe, because it's the one that goes from our last inlet basin out to the river or lake, wherever the water's getting dumped. So I'm just going to call it outfall. Alright, we want it to be user defined for all of these. Okay, so pipe C has a length of 177. Pipe B has a length of 183. And I'm just going to assume a length for that outfall pipe. It's not going to be the defining characteristic of our network. I just want it to be really big and really steep so that all the water can definitely go through there without any trouble. So I'm just going to say it's 50 feet long. I think you'll see what I mean in a minute. Okay, here's all of the starting diameters, 12 inches, our Manning's N. You notice it doesn't yet know the flow rate through any of those pipes. There's a lot of things we haven't told the program yet. We haven't told the program anything about the rainfall. We haven't told the program how big the contributing areas are. We haven't told the program what's the time of concentration. So there's still a lot of things that we have to define before it's going to be able to use Q equals CIA and calculate the flow rate. All right. Any questions? All right, so we've defined the catch basins and the conduits. Let's say, what if we did want to change an N value? So you see the Manning's N's of 0.013. That's a typical N value for concrete. But if we had a more rough concrete and we wanted to change our network to 0.014, one of the nice things you can do in the program, rather than having to type it in over and over and over, you can right-click on the column at the top and do a global edit. And so our global edit is we're going to set all of the values set to a value of, now we could type in 0.014. Okay. And so it's changed all of those without the need of us going through individually and changing each one manually. The other thing I'll mention about it's assuming the start and the stop. We can reverse that if we need to. We can reverse the node directions. That may need to be a column that we also add here. So edit. Let's see if node reversal is one of the columns we could add, because node reversal would flip it for us. Alright, they may have changed that already since the last version of the program I used. So if we needed to change which is the start and which is the stop, we'd maybe need to do that through the properties then rather than through the table. So like if we open up pipe A, I wonder when it opens up the properties table if node reversal is one of our options here. Because if you accidentally, oh yeah, here we go. See node reversal? If you activate that, did it do it? Oh, okay, yeah. So it's swapping start and stop. So we want this, yeah, I've reversed it too many times now. So I want it to go back. So now the start is 1.1 and it's stopping at 2.1. Okay. So if you draw things in the wrong order, that's how you can overcome that. This imaginary pipe that I have to put in, I have to give the network someplace to dump the water. but this outfall 1 doesn't have an elevation yet. And right now it assumes the elevation is 0, which is going to make that an awfully steep pipe. So I'm just going to open up the outfall table so I can change the elevation of that outfall. I'll tell it that the ground there is the same 235 that I've been using for all the other ground elevations, but the bottom of the pipe, let's see, what's our lowest invert elevation so far? 718.36. I'm going to say it's at 710. So it's still really low. And the point of doing that is I want to make sure that that imaginary pipe isn't a limiting factor in designing the other 3 elements in the network.
What's our invert elevation?
What?
What was our invert elevation?
The invert elevation?
Yeah.
I just put 710. The point is make it really low. All right. So now we have to define the catchments. We have to tell the program what are the areas that are going to be, like how much area is draining into this grate. All right. So yeah.
For the outfall,
Mm-hmm.
you put the elevation as 235.
Oh, did I? I thought that was the ground elevation. Let's double check. Okay, ground elevation 235, rim elevation, oh, invert 710.
I think it was 735.
735.
Okay, ground elevation 235. Yeah, that won't work. 735 would work. Thank you. All right. All right, so any questions so far? Okay, on the layout here, layout tab, there's the catchment button. And we're going to click that. Now, remember that this is just kind of like a conceptual network. We're not drawing it to scale. And if we had an image in the background that we were drawing on top of that actually was like a physical representation, like the aerial photo of the parking lot, then we could draw the boundaries of the catchment to match up with where we know the curbs are and where we know the elevation breakpoints are. But since we're not doing that, and since this is just kind of like a schematic representation, where I click isn't necessarily important. I just want to create some area to kind of, and then click, not do it, right click, done. All right. So this is now catchment 1 that feeds into inlet 1.1. And actually, the program doesn't know yet that it goes into that, inlet. I'm going to have to connect the dots, so to speak. I just drew on top of it just because that makes sense to me. So again, to get that, you go into the layout tool and then catchment, and then just draw something like some area that we're going to use to represent the contributing areas that go into each of these. Now 3.1, yes, we have an area for 3.1, so I'll create, it can be any shape. If you're using the program for real, like in a scaled basis, you'd draw these with a little bit more care than I've drawn them. All right, let's rename the catchments to be consistent with the data that we have in the handout I've given you. For example, we're calling the catchments the same name as the inlet that it goes to. And we've got known areas, known C values, and then times of concentration that were calculated somewhere else. You know, like maybe they were using the FAA method or the Kirby equation or something. So these times of concentration have been calculated or estimated external to the program, and we're going to know those. But let's open up the table for the catchment. So here in the flex tables, we'll open up the catchment flex table and change the names and put in all of the data that we happen to know. So for example, instead of calling it catchment 1, I'm going to call that 1.1 because that's the inlet it goes to. Instead of catchment 2, I'm going to call it 1.2. Catchment 3 is 2.1. And catchment 4 is 3.1. Okay. Now let's give it the areas and the C values that are in the table there. So 2.2 acres, 1.2 acres, 3.9 acres, and 0.7 acres. The C values we can get from the table. Times of concentration. This column is in hours, but the data we have is minutes. Rather than converting it with our calculator, let's right-click on that column, units and formatting, and we'll switch from hours to minutes. Now we don't need to see 3 digits afterwards, so I'll just maybe change that to 1. Click OK. Alright, so now it's time of concentration in minutes, which is more convenient. So 11 minutes, 9.2 minutes, 13.7, and 8.7. Okay, there's one more thing that we have to do. This outflow element, this is where we tell the program which area is going to feed into what inlet box. So for instance, 1.1, we click on the side there, that little dot, 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 the ellipsis, and now it's saying click the inlet the water is supposed to go to. So I just click there, and now you can see that little dotted line. It's connecting the area with the inlet to the network. So I'll do the same thing with 1.2. Click on the dot, dot, dot. Now it's saying, all right, click on the box that area 1.1 feeds into. So there's that relationship. So go through and define the connection. I maybe should have made them even further apart so you can see the dotted lines.
How would you know time concentration from hours to minutes again?
You right-click at the top, units and formatting, and then you change it from hours to minutes. And by the way, if you change it back, I think it'll do the calculations for you. But we want it to stay as minutes. Are there other questions? All right, so think about the rational method. Q equals CIA. We have the C and the A, we don't have the I yet. So on the one hand, there's the hydrology. The only thing missing from the hydrology is the rainfall. On the other hand is the hydraulics. So for the pipe hydraulics, we've defined the shape of the pipe, the slope of the pipe, the material and roughness, the diameter. I think we've given it all of the hydraulic data that we need to, once the Q is generated from the rational method, it's going to tell you how full the pipe is. Is it 100% full, 50% full, 200% full? So that's going to be the output of the analysis once we generate the rainfall data. All right, so now we have to define a rainfall event. So here under storm data, let's do storm data, and then instead of picking one of these are kind of like pre-existing rainfall estimates. We're going to create our own user-defined storm. So here, new storm data, new user-defined storm. All right, and now this is where we're going to type in the data from this table. So like this stormfall data, we're going to put into the program, and it'll create a curve based on that. So add a return period. I'm not sure what storm this relates to. Let's call it, it's the 10-year storm. It's the only one we've got, but okay, add range, Oh no, we don't want that. Yeah, add duration. All right, so we want to have a 5-minute duration. We want to have a 10. I don't know if the range, if we could automate that, but we want to have a duration for 15, 30, and 60. All right, and now we have to fill in the intensity, inches per hour, in stereo. Yeah.
So, return period, what should we put in that for return period?
Doesn't matter. We've only got one curve, and it doesn't say in our draw, oh, if that's a 25 or a 10-year storm, it's just, that's our design storm. So why don't you call it 10? Let's call it a 10-year storm. And the only reason it matters is when you say analyze the event, you're going to have to know to pick the 10-year storm. But we're only going to have one storm to choose from. We could, if we wanted, also give it a column for the 2-year storm data and the 5-year storm data, and then look at how this network is performing in different storm events. But we're just going to analyze it according to one storm event. So type in the intensities for each one of these. All right. So this curve isn't exactly as smooth as what we have in the handout, but it'll do. It's fine. All right. So we've given it the eye. So we close that. All right. So now we are going to have it do a scenario.
How does it save the data for our storm?
As soon as you close a box, it's in there. So it kind of it saves it by default. You see how it's in the database. You don't have to click save or anything like that.
Okay.
Anytime you make an adjustment, it automatically saves. All right. No, that's not it.
That's the same one I had.
All right, go into, okay, for the storms, global storm event. Okay, yeah, so we're going to tell it to choose our 10-year storm. Yeah, so we defined the storm under storm data, and then global storm event, we have to tell it which storm we want. So we picked that 10-year storm that we just created, and now if you click compute, convergence was achieved. That's good. It would have made an awful noise if it didn't work. So now what we're going to do, we get some warnings here. Does not meet maximum velocity constraint. Conduit discharges above design discharge. And so remember, all of those pipes just to start with were 12-inch diameter. And what it's telling us is 12-inch diameter may not be the best size for all of these pipes. Let's look in the flex tables just to see why. So if you open up the conduit flex table, look at this percentage, the flow to capacity. So when we did the Q equals CIA, we got a design flow rate that's going into each one of those inlets, and then it knows how much is in each pipe. So pipe A, for instance, is going to have 5.77 CFS, but its capacity, based on the slope and diameter, is only 4.68. So since the actual flow is greater than the capacity, then that means that the pipe is undersized. We have to make the pipe larger. Jeffrey, do you have a question?
Yeah, I have an error related to the outfall. It says the user-defined length should be greater than 0.
Okay, change the user-defined length to a value greater than 0.
I'm trying to get some length.
It doesn't matter. Just give it some length. If you open up the flex table for the
Outfall.
conduit, yeah, the outfall pipe, just give it some length. You know, it's not on our sketch, so we don't know how long it is. It's just the water goes somewhere. We want to make sure that A, B, and C are the right size. All right, so let's go back into the conduit table. So all of those pipes need to be bigger than they are right now. Which of the pipes is the most undersized? Like, which of the pipes would fail first? C. That's exactly right. How did you know C is the one that's the most undersized?
It's the percentage is the highest, so.
Good. Yeah, it's 344%. So let's make that 18 inches, and let's try 16 inches for all the rest. Okay. Oh, actually, the outfall pipe wasn't undersized, but we have to remember our rule is that pipes can't get smaller. So I'm going to make the outfall pipe also 18, because we couldn't go from an 18 in C towards a 16 at the outfall. So you change the diameters, and then you don't even have to close that. You can just click compute again, and then now the percentages are updated. So pipe C still isn't big enough, but it looks like we maybe made pipe A a little bit too big. Like maybe, I wonder if a 14-inch would have done okay for pipe A. So I'm going to just look at pipe A for now. I change it to 14, compute. Yeah, a 14-inch pipe would be fine, because look, it's at 81% capacity. So if I want to do optimum, I know my user-defined sizes, like the sizes that are available. In your homework, I tell you, here are all the pipe sizes that are available. These are the increments that you can count on having the ability to purchase. So we're going to stick with a 14-inch for pipe A. Pipe C still isn't big enough. 18 doesn't get us where we need to be. So what is 20 the next size after 18? Yeah, let's try out a 20. Okay, so we're going to make pipe C a 20-inch. And if we make pipe C 20-inch, then that means our outfall pipe also has to be 20, even though hydraulically it's not even near capacity because we made it so steep. How is pipe B doing? 93%. That's pretty good. That's close enough to 100 that it's unlikely. A 14 isn't going to work, but let's just prove that to ourselves. 14 is going to probably be too small. So compute. Yeah, so the 14-inch pipe is undersized. So 16, and I think we are optimum. Compute. Yeah. All right, so we know that this is the optimal design because if we make any of these pipes smaller, then they're going to be over capacity. You know, what other optimization could we do? Well, you know, if you were actually designing this network, you could choose different depths for the inlet boxes. You know, like if you're having, the standard assumption is maybe you'd put your inlet 5 feet underground. Well, if it turned out that like one of your pipes is just barely over capacity, one way to give it more capacity is to raise the upstream end of it so that you've made it steeper. So maybe most of your boxes have a 5-foot depth, but then this other one is only 4.5 feet, so that you've now made the pipe steeper and the pipe diameter doesn't have to be increased. Jeffrey, do you have a question?
Yeah, I did the calculations, and I'm trying to figure out where on here it says that the design works.
It's just you look. It's not a yes/no thing. It's like you're looking at the column where it says flow to capacity. That ratio in percentage is telling you how much water there is relative to the flow capacity of the pipe. So it's the ratio of this, which is the rational method, Q equals CIA. It's getting the flow from Q equals CIA, and then it's getting this capacity from Manning's equation. Does that answer your question?
I believe so.
Yeah. So you check this column, the flow to capacity column. All right, we are out of time. It's 9:46. So I think with that very brief overview, what you're going to be able to do now is create this entire network and optimize it. What you need to turn in is basically 2 annotated drawings. As I say in the homework assignment, the 2 maps that I want to see should have the pipe diameter, the flow rate through the pipe, the percent full, and you can do those annotations the same way that we did like with StormCAD, where you could right-click, New, Annotation, and then you choose for a conduit, for example, maybe we're going to have diameter as one of our annotations. And so then this would be D equals, and I click Apply, and it put it right on top of it, so I change the offset maybe to offset it 3 vertically. Now, no, that was horizontally. 3 vertically, now it's above it. So I give you some illustration of the annotation that I'd like to see. And in the handout assignment, the assignment handout, there's also a couple of videos where I show you a summary of how to set it up, how to prepare the image for printing, and so on. I wish we had more time. I usually get to do this demo in a 75-minute class, so I apologize if we went through it quickly. The recording is online if you want to take another look at anything we did. Let's just finish by looking at the announcements. Remember that on Wednesday we won't be here in class. It'll just be a video that I send you the link for. And then this homework that's related to the rational method and StormCAD, that's due a week from today. All right, so I'll see you on Friday. Have a good one.